Good morning, good afternoon, good evening to our international audience for today's webinar on HIL-based wide area monitoring, protection, and control, research and development, and testing. So I'm very excited today to present to you myself, Tom Kirk from OPAL-RT, who will be moderating our keynote speakers, Mario Poloni from the École Polytechnique Fédérale de Lausanne in Switzerland, and Luigi Vanfredi from KTH Royal Institute of Technology in Stockholm, Sweden. It's just a coincidence that their names are Mario and Luigi, but no, they are not Nintendo characters. They are very serious presenters, so we hope everyone appreciates this link. So the webinar outline will simply be a brief introduction on the topic, followed by some examples from some clients and the software that we offer, followed by 20-minute presentations by each of our keynote speakers, and then a question period. But just note, stay till the end, so like that you can complete the survey where we will actually ask you what topic you would like to hear about in the next webinar. So when I was doing research on this topic, I found this introduction, which has been cited several times in literature, and I think it gives a perfect description of what wide area monitoring, protection, and control are about. So it involves the use of system-wide information and communication of selected local information to remote locations to counteract the propagation of large disturbances. And of course, synchronized measurement technology is important, as we all know. And the hope is that these systems will really serve to reduce the number of catastrophic blackouts, improve reliability, security of the bulk power system. So these are very lofty goals, and I'm excited to present to you the speakers that will talk more on where this is going. So what is the main motivation behind WAMPAC? Well, number one, the power grid hasn't been updated in decades to actually meet the growing demand of energy on the grid. So we end up with these highly stressed systems that also have added complexity with the introduction of DERs. And as a result of DERs, you have reduced system inertia. And as a result of those, you end up with some increased instability, and at the end, we're all worried about less reliability and security. So we always point to the 2003 blackouts in Canada and the United States, as well as Italy. In fact, in the North American report, they really pointed to the lack of real-time functionality as a root cause. So to no one's surprise, synchrophasers were pushed to the front. And as we know, they have a significant advantage over SCADA, whereas, for example, in this wind turbine oscillation example, a traditional SCADA system can't really capture those oscillations. So what happened is the DOE and industry partners, at least in North America, invested hundreds of millions of dollars to really push this technology and to effectively field test it. So now in North America, there are over 1,500 PMUs providing a reported near 100% visibility. What does this progression look like? Since 2009, we have still a respectable number of PMUs monitoring the grid. They double in 2012 until 2015. I mean, they're blanketing the most populated regions of North America. Now, these devices and these systems, they are noteworthy because not only do they go between physical locations, they go between jurisdictions, organizations, companies. So it's not just a technical issue implementing these things. It's political, it's organizational, it's law. And what are the effects? So this project has had quite a bit of success. They've dealt with major players in the industry, including Entergy, Duke Energy. So what the players have found is that they've actually been able, in many cases, increase system reliability, increase asset utilization and efficiency, power system efficiency, and organizational efficiency. And they've done that through introducing several real-time capabilities as well as study mode capabilities, many of which can be tested using hardware-in-the-loop simulation. What strikes me, though, is it's not just about the equipment you connect to the grid. They found that it's really also about the communication networks. So if you don't have the resources in place you can spend up to $180,000 per PMU, which was found in another report that's cited. And also cybersecurity has come to the forefront. It's not going away. So this has become even more technically challenging than simply implementing synchrophasers at selected substations and railing information. You actually need to pay attention to all these various aspects, especially if you want to eventually implement control. So we'll stop briefly so that our attendees can answer the first poll. So we'd like to hear from you. What are the challenges you face when working on wide area applications? And we'll give you 15 seconds. So we see some fluctuations in the polls. This is normal. But it seems that the top 3 categories are certainly the most popular. So we'll continue on. So I'll explain very briefly real-time simulation setup and software in a couple examples. So typically when we talk about real-time simulation, we will take a simulator, effectively a computer with an FPGA or many FPGAs, and we will load a real-time model representation of the system onto the simulator, and we'll interface this with all sorts of hardware and software, including PMUs, relays. We'll also, in several cases, want to keep an accurate time synchronization using either GPS clock, and as I was discussing earlier with one of our presenters, there's more coming out on that in the future, so look out. Now, you may not actually get the effects that you need from simply connecting these devices with a low voltage interface. You might actually want to simulate the near field effects, so in many cases, a power amplifier may also be required. Now, that's expensive. So what if you can get away with actually modeling these real devices in the simulation? So this is something that is definitely coming more and more into the forefront. As you saw on the map of the United States, you don't want to have 500 PMUs in your lab. And of course, the communication network, as I mentioned, is incredibly important. So how do you simulate that aspect? And we know there's certain researchers who have used OpNet. We're looking at scalable networks too, since it seems to be a very robust real-time solution. And at the end, you're looking to connect to applications, whether they be visualization or even controls. So these are some of the applications we've connected to in this sort of application. And in terms of software, we offer eMegaSim, which is electromagnetic transient simulation. So this type of solution is based off MATLAB Simulink and SimPower systems. It's very popular in universities and with users that already know the simulation tool. And it's nice because you're able to actually automate many functions, and as you'll learn from Luigi, hack it. And the benchmark for this software, so we mentioned that it can do up to roughly 400 three-phase buses. Well, this is actually a network that was simulated using eMegaSim, delay-free, so no delay introduced between processing cores on the multi-core computer. And it's effectively a regional distribution network with 750 nodes in Italy, a real one. So you can look up that to learn more. And then we have HyperSim, which was actually developed by Hydro-Quebec, and this is also a very capable software. It's capable of modeling thousands of buses. It automatically distributes simulation across potentially hundreds of processors if you have such a supercomputer. And it also supports automated testing. And finally, which is a really interesting software for people looking to wide area research, is ePhaserSim. So this is an electromechanical real-time transient stability simulator. So unlike the EMT software I just mentioned, it only supports a 10 millisecond time step. So you're actually able to import PSSE, SIME or DigiSilent power factory networks directly into that. You can actually model other functions in OpenModelica. So you can actually bring in your own custom generator models or transformer models. And it allows you to do this sort of simulation where you effectively model a wide area and you can model potentially hundreds of PMUs to connect to a controller on the other end. So this is a more recent product, and we've actually succeeded in finding several clients that in industry and in academia that have found this application interesting and useful. So we're looking forward to seeing more results from them. One of those clients is TMB Research, and in fact they have a setup where they use ePhaser SIM to test and develop an out-of-step protection control system. So they've done that using C37-118 streams that have been sent via dedicated relays, and actually from the simulator as well they send commands to generators using Goose from the controller. It's a completely closed-loop setup. Using HyperSim, this is recent, in NASP we presented a bit on PMU pre-certification. So certification is very expensive, as some of you may know. So the idea here is, what if you use a real-time simulator to pre-certify your PMU prior to sending it to the lab? So there's two ways of doing this. Well, you have the one where you're able to simulate the near-field effects with the amplifier. You can also go via a low-voltage interface. And in fact, what our results showed at NASP was they may not be perfect, but the results will likely show you if your certification is going to fail. And in some cases, for some tests, they're very reflective. So we're still working on developing more functionality on that end, but it's very promising. Now, some of you are used to seeing these things in your lab or in the field, and you can't really get inside them. They're closed systems. So we've actually partnered with National Instruments to provide an open system for IAD development. And the idea there is, effectively you get a box, but you're able to open the box, you're able to change all the modules within, in this case, a compact Rio. And not only that, you're actually offered a library that's already been tailored for the power system industry. So you have the communication protocols that are used in the field, you have tools that you can take, you can modify, and I know Luigi's going to talk about his open source projects, so this is definitely the way of the future, and we're looking into giving users even more options when it comes to actually making hardware. So it's not just about delivering a simulation tool, it's about delivering the actual hardware that can be used to perform work. So that's my bit, and next up we have Mario Polone. So he received his Master's in Science and PhD from the University of Bologna in Italy. In 2005, he was appointed Assistant Professor in Power Systems at the University of Bologna, where he served as a Power Systems Laboratory Professor until 2011. And currently, well, he's since moved to the Swiss Federal Institute of Technology in Lausanne, Switzerland, where he is the EOS Holding Chair of the Distributed Electrical Systems Laboratory. In 2013, he received the IEEE EMC Society Technical Achievement Award. He is the editor-in-chief of his Elsevier journal, Sustainable Energy, Grids and Networks. His research interests are in power systems with particular reference to real-time monitoring and operation, power system protections, power system dynamics, and power system transients. And I should note he is the author or co-author of over 220 scientific papers. So without further ado, here is Mario.
Thank you, Thomas, for your kind introduction. I hope that you can see my screen. The title of my contribution to this webinar is Hardware in the Loop Architectures and Application Examples. So my presentation is essentially split in two main parts. In the first one, I'm going to talk about the elements that your HIL architecture should take into account when it comes to the simulation environment that you're going to set up. And the second one, I'm going to show you 3 application examples related to one-pack systems. The first element, it's how to embed and how many PMUs you can embed into your HIL setup. So this is the typical example that has been shown by Thomas in his presentation. So essentially you have your real-time simulator, which is containing the real-time network model. So you're outputting your signal, and you have real PMUs with or without amplifiers as a function of the kind of signals that you have. You have your network switch, or you can imitate your telecom systems. Then you concentrate your data, you have your application, then you feed back your control signals back into the model. So The problem of this kind of setup is that it's very expensive. It might be also limited by the number of outputs that you have in your system. The cabling can be really complicated. The advantage is certainly that you are testing real PMUs, and the computational complexity is not so high in the sense that your network model should not take into account PMUs. The second approach is to embed the PMUs into the model that is running on the real-time simulator. So it's much more cost-effective, so you're not limited by the available analog outputs and the available hardware, namely the PMUs. But, of course, there are two problems with that. The first one is that you are adding computational complexity into your model. And the second element is that you should be able to say that your software PMUs are metrologically identical to the PMUs, to the physical PMUs. And actually, there are not so many people that have transferred the synchrophasor extractional algorithms into the real-time simulator with the metrological performances which are identical to the ones of the real systems. So we published a couple of papers on this subject where we took a Class P PMU that we developed in my laboratory. Actually, it's a Class P PMU that you can deploy into a National Instruments compact reel, so I was very pleased that Thomas was mentioning that. And actually, you can also embed into the National Instruments automation system. It's compliant with the C37 118 2011 Class P. So it has a TVE in the range of 0.02%, so it's extremely performing in this respect. It can have reporting rates up to 10,000 frames per second. Yes, so we can output a frame essentially for each raw sample which is entering to the PMU. But normally we reduce this to 50 or 60 frames per second. So essentially we can run this synchrophasor extraction process into the simulator. And just to give you some numbers, we can stack something like 10 to 12 three-phase PMUs sensing 3 voltages and 3 currents into one core. So essentially you have 10 PMUs per core, just to give you a rough idea of how many PMUs you can stack in your hardware in the loop. The second element that you should take care of is the time synchronization. So in particular, you have to be sure that you distribute your time sync into the various modules of your HIL setup. In particular, in our setup, we are using a Spectracom TimeSync PCIe that is capable to distribute towards the various targets of the time synchronization. Why you need that? Essentially for 2 reasons. The first one is very obvious. Essentially, you wanted to distribute the time to the PMU to time tag your synchrophasor. That's obvious. The second reason, which is less obvious, is that this gives you the possibility to time tag the computation of the simulator. Therefore, you can tag which are the outcomes of the integration of the differential equations into the simulator. And this gives you the opportunity to time tag the true information that you have into the simulator and then compare to what you are sensing outside. And this is something that you cannot do in a real world, because in a real world you don't know which are the true state of the system. And this is something very usual. I will come back to this point later. The third element that you should take care to model are the models of the sensors. So I'm not going to talk about linearity, bandwidth, and saturation, because this is something pretty standard. You can find libraries which are capable to represent this kind of aspects. What I'm going to talk about is how to embed the noise of the sensors into a real-time simulator. So essentially you have 2 sources of noise. The first one is a grid noise, which is a Gaussian and zero min. It typically represents a few percent of the RMS of the quantities that you are measuring. And the second element you should take into account is the gain and phase error noise, which are introduced by the sensor. Now the problem is that these gain and phase errors are typically expressed into polar coordinates. You have to transform these quantities into a time domain noise, which is added to the outputs of your quantities, which are sensed by your sensors. So essentially come up with this formula, which is highlighted in red, where delta AN and delta phi-n are randomly generated magnitudes and phase noises added to each sample. So essentially, these 2 quantities are calculated according to the type A or type B uncertainties of the sensor, assuming respectively Gaussian or normal distributions. These are the typical nomenclatures which are used by the the guide for uncertainty measurements. And this is how we did it. So essentially, you can embed these kind of sources into your of errors or noise into your sensors models. Well, what's the output of this kind of stuff? Well, essentially, by adding this noise, you are creating noise inputs in your PMUs, and these are examples of how these noises are affecting the amplitude and phase estimations of a PMU. And this is actually how resilient is your synchrophasor extractions against the presence of the noise due to the sensors. So let's jump to the part on the applications. So the first application that you can imagine into one-pack systems is the, between brackets, traditional set estimation. In this case, what you're interested is to validate PMU-based set estimation, so a linear set estimation process. So that's the hardware setup. So you have a GPS clock which is distributed to the real-time simulator. So you can time tag the true system state. Of course, you can do that only if your system frequency is constant, and in particular, if it is equal to one of the bins of the DFT. So in this case, you can really tag which is your true system state. At the same time, you're distributing also the clock to your application. In this case, is the PDC. Where you also do the aggregation, and then you're pushing the data frames to your application. In this case, is a simple set estimation process. It can be either a least square process or a Kalman filter. So that's the application. What can you do with that is that you can characterize the performance of your set estimator. Why? Because you can inject bad data into your simulator. You can inject biases in your sensors. You can also remove some of the data frames, so you can see how robust is your set estimator against these kind of failures into the sensing system. So here I'm going to show you how we did this setup when we have dynamics which are embedded into the nodes. In particular, we're embedding dynamic loads or distributed generators by using controllable current sources in this specific case. So considering the true system state, since we're not changing the system frequency, essentially you can compute exactly one of the DFT bins, and this is what you can baptize as true system state. So this is what the simulator is computing, which is then fed to the sensors, which are then adding noise, nonlinearities to that, which are then censored by the PMUs and then estimated by your set estimator. So actually you can metrologically characterize the whole chain from the true system state down to the estimated ones, and then you can do a comparison of the performances of your set estimator. So this is what you get. So we are using a true system. It's a distribution system that was the target of an FP7 European project. Actually, it's a system located in the Allianders grid in the Netherlands. Here you can see the configuration. It has 18 buses. It's a 10 kilovolts line-to-line system. We also have a distributed generation. And we are sensing 10 out of the 18 nodes with PMUs. These were real PMUs. And before going into the real field, we're running a real-time simulation to characterize the performances of the set estimator. So through the process I was describing before, we were able to characterize the means and the absolute errors, the means and the standard deviations of the absolute errors in the magnitudes and phases of the set estimates. So here you can see the four quantities, namely on the top you see the voltage magnitudes in per units, means and standard deviations, and on the bottom is the same quantities, means and standard deviation for the phases of the phase to ground voltages. So you can see that we are obtaining quantities which are jittering in the range of 5 times 10 to the minus 5 in per unit for the amplitudes, and almost the same quantity also for the phase. So essentially, after running this characterization, we're saying to the operator, look, if you are going to have this noise level and you're going to deploy this sensing infrastructure, these are the kind of uncertainties you can get in your assessment of the system state. So it's a kind of performance assessment. So the second element that we were able to test was time latency. So essentially, we were interested to characterize which were the latency from the moment we were collecting the PMU measurements, the moment these measurements were entering into the PDC, and the moments these measurements were pushed into the real-time set estimator, and the moment the set estimator was capable to estimate the system state. This is important if you are interested to close the loop, as we'll see in a while, if you wanted to do voltage control or fault handling applications. So these are the kind of information we were interested to characterize essentially 3 latencies in these 4 time instance. And these are the kind of results that we get. So essentially, we're able to compute, to assess in with the HIL architecture that was describing the 3 cumulative distribution functions of these 3 delta t's. So essentially, we're able to close the from the moment we were sensing, the moment we are estimating the state. This was essentially providing us an average latency of 53 milliseconds with a jitter of less than a millisecond. And this is a kind of information which is particularly useful, especially if you're interested to play with fault location or relaying applications. So you should be able to characterize which is the jitter of your information data flow. So the second application I would like to show, it's relying on the system state estimation. So essentially, we are assuming to know the system state with a pretty high refresh rate, and we would like to use this information to do voltage control. So essentially, we have an online centralized optimization tool, which is computing sensitivity coefficients. You know, sensitivity coefficients are essentially how much a voltage is varying in a given node as a function of all the injections. So these coefficients can be computed as a function of the system state in a closed form. We have a paper that has shown how to do that. And now we would like to see how we can distribute these sensitivities in, how we can use this sensitivity to distribute the control through broadcast signals. So essentially, we like to distribute broadcast signals to aggregators, which are essentially distributing them in the form of broadcast signals to thermostatic controlled loads, so essentially traditional demand-side applications. So essentially, we are broadcasting signals per node, and these broadcast signals are unique per each network bus. And we would like to see how this application, which is actually described in these 2 iterative transaction pairs, can be characterized in terms of latencies into the hardware in the loop application. So essentially, we have the same setup as before. So we have a real-time simulator, which is embedding the network model, the sensor models, and the PMUs. On top of that, we also imitate into the network model the thermostatic controlled loads and the controllers, which are playing the game of these broadcast signals. And at the same time, we're embedding into the simulator non-elastic demand, because PCLs are, on the contrary, elastic demands, and active generations, in this case, non-controllable PV resources. So essentially, we send PMU data to a workstation, which is containing a PDC and a set estimator. The set estimator is feeding the demand-side centralized optimization tool. In this case, you can see this acronym GECN. The GECN stands for Grid Explicit Congestion Notification. It's a kind of protocol that we're using to compute the broadcasting signals for the demand-side management. So essentially, we compute the sensitivity coefficients, we feed an optimization program, and then from the optimization program, we compute the broadcast signals per node. Then we distribute the broadcast signals through a compat trio that is then feedbacking this into the analog inputs of the real-time simulator, and we close the loop. So everything is GPS synchronized. Again, we are using the same distribution system we were showing you before. So it's the same network of Alliander. Again, the same configuration. Here you can see the aggregated power injections, active and reactive power. You can see that there is a big hole in the middle of the day. Why? Because this is the typical effect of the PV injection. So you can see a kind of duck curve, you know, the duck curve from the California ISO. So it's, here you can see it, a scaled version into a distribution network. So here you can see the effect of the performance on the voltage control on a 24 hours profile. So we were running a real-time simulation for 24 hours. So it was a simulation that took 24 hours to be completed. So on the top you can see bus number 3 is a bus where you don't really need to do voltage control because the voltage is always within the bound. On the bus number 12, on the contrary, you can see the effect of the GCM controller to keep the voltage within the bounds. And you can see actually the effectiveness of this control loop into this HIL simulation. So the second element we were able to add was also the time latency. So on top of the 55 milliseconds I was showing you before, we add a further 10 milliseconds that were needed by the GCN controller to compute and solve the optimization problem and then send the broadcast signals to the various nodes. So you can see that during the 24 hours, the computation due to the GCN was always kept constant and bounded within 10 milliseconds. Last application that I would like to show, it's about the use of this framework to do fault location. So we were publishing a paper, actually it's a nitrogen transaction power delivery in 2016, where we're essentially using set estimation processes to locate the faulted line. So essentially the principle is very simple. We're running parallel set estimators. In these parallel set estimators, we're able to add a virtual bus. This virtual bus essentially is a bus that is containing the fault. So if you don't have a fault into the system, essentially all the set estimators that are contained in this virtual bus are providing you the same results. So if you quantify the weighted measurement residuals of this set estimator, essentially you're providing more or less the same kind of numbers. As soon as you have a fault in your system, for instance, here I'm adding a fault in the line number 2, actually only the set estimator number 2 is containing the right topology. Therefore, the weighted measurement residuals of the set estimator 1 and 3 will explode, literally. And only the WMR, which is briefly recap on the bottom left side of the slide, is almost kept a value which is comparable to the conditions that you have before the fault. So this is the metric which is used to distinguish between which is the set estimator with the right topology, which is essentially telling you which is the correct line that has the fault. So again, we are using the same distribution feeder of Aleander to run these kind of experiments. In this case, we're using also sensors with the right characteristics that were corresponding to those installed into the system. So here you can see the weighted measurement residuals of the various set estimators. You can see that we have 17 set estimators running in parallel. Yes, you can ask me, yeah, but this is computationally demanding. No, because we are doing a linear set estimation, so it's computationally inexpensive. Each one of these set estimators is taking microseconds to be executed, so you can run them in parallel without any problem. So you can see here we are doing a three-phase fault in the line 1316, with even a high impedance fault, was 100 ohms. And you can see that we are actually having the lowest weighted measurement residuals exactly on the set estimator that was contained in the virtual bus on the line 1316. Which is the difference between these two figures? Well, on the left figure, we were using the noise levels of the actual sensors. On the right-hand figures, we're using noise level 10 times worse than the ones of the actual sensor installed into the feeder. And also in this case, we're able to locate the fault. So this is the kind of application you can also imagine to deploy in your HIL. So for this specific case, we're able to test fault location applications to and validate whether our process was able to detect and identify and locate fault types which are symmetrical or unsymmetric, namely a single phase, two phase, three phase. We test fault impedance until 1,000 ohms. We're capable to test radial measure systems and neutral that were isolated or grounded. So essentially, we were capable to characterize the whole performances of the set estimator and also test the latency that in this case was always kept below 120 milliseconds. So that was a very important outcome for the grid operator to characterize the fault location application in case they wanted to use it even for relaying applications. So in summary, let me say that HIL are fundamental tools to run performance assessment of PMU-based processes. Fundamental elements out of the grid model to be represented are time synchronization, synchrophasor estimation processes implemented in metrologically characterized PMUs, sensors in terms of noise, saturation, linearity, and bandwidth, and then the potential applications that you can feed once you have fulfilled these elements in terms of representation are PMU-based real-time set estimators, centralized optimal voltage controls, or what I've not discussed, line congestion management, and fault locations. Of course, there are much more applications you can think about, but we focus only on these specific ones. In case you are interested in more details, we can definitely run more detailed webinar on these aspects. So thank you very much for your attention. I'm looking forward to see your questions.
Thank you, Mario. So before we proceed to Luigi, we're just going to run a second poll. So the question in this poll is, in your opinion, what is the primary application of real-time simulation for wide area monitoring, protection, and control? So thank you very much for your time on the poll, and we'll proceed to our next speaker. So We have Luigi Vanfredi, who obtained his Master's in Science and PhD in Electrical Power Engineering from Rensselaer Polytechnic Institute in New York, where he was actually awarded the Charles M. Close Award for his research and teaching work. He became an assistant professor at the KTH Royal Institute of Technology in Stockholm, Sweden in 2010, and in 2013 he obtained a tenured associate professor position. What's interesting is from 2011 to 2016, he was actually an external advisor on science, as well as a special advisor in R&D and strategy and international collaboration at the R&D division of Statnett SF, the Norwegian transmission system operator. So he's not just an academic, he's worked in the real world, which is nice. Not to mention, you're going to find out, he is an advocate and evangelist for open source and free software. So he'll talk a bit about his GitHub, and with no further ado, here is Luigi.
Okay, hi everybody. I hope you can see my screen. Can you see it? I guess so. Okay, I'm not seeing any feedback from the chat, but I guess we're going.
Yeah, it's perfect. Thank you.
All right, so I call my presentation Taking the Next Step, because it says in the title of the webinar is the next step in Hardware in the Loop. So how can you take it? And to take it, you have to implement, test, and to implement and test, you need some tools to do it. And the presentation is focused more on real-time control and protection, but we have a little bit of monitoring also. This is the webinar. Yes, there is Mario and Luigi, and we are indeed Nintendo characters. It's a picture that one of my students added to do. I think he's listening, so he must be laughing right now. Okay, so I'll tell you how we set up the lab. It's been almost 6 years now. So I'll give it in a historical context and how do you do work with this, and so a little bit about modeling, then applications, and then some tools that you can use. And I want to thank all of my students. You will see a lot of papers by Almas and Maxime, and some results of the rest of the people in the pictures, and actually I wouldn't be able to do anything if it wasn't for their effort. So this is more a presentation about their work and about some of my ideas. And most of the work that you see here, it has been funded through these projects that you see listed there. So yeah, the money has to come from somewhere, doesn't fall from the sky. So we work in several areas. The fundamental technologies that we work in our lab are on modeling and simulation. The technology itself, so how do you do simulations with open languages and things like that. And sensors and data infrastructure, that's mostly on the PMU stuff. And then we develop applications for these different contexts like monitoring, control, protection, predictive tools, and some data analysis. So let's see, we have this lab, of course, Mars Lab, and it's also the name of my research team. So in 2010, I arrived to KTH, and I wanted to set up a lab. So I started setting up this around 2010, August, September, something like that. And not a lot of people was doing this stuff in power systems. Of course, it's a 30-year-old field if you talk about the automotive guys or the aerospace guys, but a lot of the people in power systems has seen this effort as unnecessary or useless, and this I call them the experts. So I actually had to write a little document to show, like, okay, why doing hardware in the loop is important. And you can, I'll send out the slides, and you can actually click there and take a look. But it was, so you can see it under a historical context. And so I started the procurement process without knowing too much, unfortunately, but that's how you start. And somewhere around March, April, we got the lab. So actually Almas and I and a couple of hourly paid technicians that will help us sometimes, we implemented the first lab. And this was more or less how it looked like back then. It doesn't look that much different right now, except that it's more organized. But this was kind of like the idea of what we wanted to set up, that we wanted to do monitoring, control, and protection. And this part over here, that's actually the work that we wanted to do, seemed pretty far at the end of 2010 and during 2011. So actually we wrote a paper, or I wrote that paper mostly, about how we have set up the lab, and we also wrote a paper about the first experiences on trying to do monitoring. So the first paper here can tell you a little bit about what I was thinking about and the justifications of setting up the lab, and actually was a good experience as for the next implementation of the lab, using the same hardware and stuff, but setting it up better to do experimental work. And then this paper showed like how you could use some tools available to do WAMs, but actually it turned out to be completely difficult, very difficult to do that approach. So actually it helped me understand the needs of kind of the environment that you need to develop prototypes in a lab with students and etc. So it was really a proof of concept stage or period that you can think about. So now post 2012, this is more or less how it looks like. So we have the real-time simulator. We have a bunch of amplifiers, as it was shown, where we interface all this hardware. And we have some PDCs that are from Schweitzer, where we can gather the data from the lab and also from outside. And we have other networks like the process bus network, so that we can use sample values, and the station bus, and those talk directly to a simulator, very luckily. But back then there was nothing to do simulated PMUs, and actually we tried something. I didn't put the reference, but I'm glad that Mario has done it, because this is really a lot of work to do this, but sometimes it's necessary actually. But after or during 2012 and onwards, our major focus was both developing the applications of using real-time PMU data and the tools related to being able to build those applications. So we have here some tools that I will briefly mention later, but you can take a look at this paper that actually gives you a little bit of overview differently from what I presented in 2011, which was a 2-year experience more or less, and now you're talking about like a 3-4-year experience after that. And this is how it looks like. You see it's a little bit less messy, but the nice thing you see here is a bunch of compact rios, which is the things that we like to use more than anything else. You see here a back panel where you can do all the interfacing between all the mess of cables that you see coming out from the simulator to here. Here is the PDCs and other software. These are targets. This one over here, this one over here. These are extension chassis for additional I/O, because remember, we didn't have abilities to stream PMU data back then. So I mean, this is how I thought about it, and this is what we still have, because we don't have those libraries. And then you can see the GPS antenna coming here, feeding in the substation clock. This is a PMU. This is our relays PMUs, and this is on our substation equipment. And you see some other substation, some testing equipment. And then this is all the workstations where the students can actually be inside there and be close to the equipment. And there's a big AC, because you need to keep these babies cool. And there is a big door between these sitting places and this simulator, because the cooling plus all these machines are noisy. And these are things that we learn among time. Also, that you need a cage so that people don't get in and steal your stuff. So you have to take a look at this in a historical context, that we started more or less 6 years ago, and you have to learn a lot of things on the process. Okay, so how do we perform scientific experimental work? To develop, implement, and test PMU apps. So my main beef with the whole research that I used to do and which people used to do is that you don't have really a control environment to do experiments. So when I set up the lab, it's because I wanted to do an experiment 100 times and analyze the results of an application statistically and do it under near real conditions. So you're using all the same devices, all the same protocols. So if you're going to deploy it in the field, provided that your simulator model is accurate enough, well, pretty much things will work. So people cannot claim that my stuff only works on the paper, but we're actually taking that step extra. And to do that, here's a little flowchart of how we work. Okay, so you have to develop a model, and I will show you one of the active distribution network. Then you need to configure the model by going into the backplane with the analog outputs, or how Mario explained with the configuring the streams from PMUs, but in this case we configure the analog outputs and we feed in either amplifiers or directly the PMUs through the low voltage interfaces. All of this equipment has to be configured, okay? So you have to program, not program, but you have to download firmware for the compact radios or for this, and you have to configure it, and then you have to configure the PDC to read the data. So it's not like plug and play and go. You need to do a lot. So to stream the PMU data, as I said, you have to configure all the PMUs, and then you have to create something called output streams. And these output streams actually is the basis that I use to decouple what it is a PDC, which I think it should be left alone and do its job of concentrating a time alignment, and what is an application development environment, which could be any workstation located anywhere, and be able to read this stream and use the data. So how do you implement a new application? Well, it turns out that there was not much back when we started. There was OpenPDC and it was really hard to do. So we implemented different kind of mediators and toolkits. And so we use these tools that we have developed in-house and with collaborators and so on to be able to make, for example, in this case, the application is just a display for the same model that we have here. So during the development, you more or less go through this circle over and over again, and you fine-tune your applications under different experiments. So you can remove a load, remove whatever you want. You know, you design the experiment yourself, and you can do that experiment 100,000 times if you want to, or if you have the patience. So I think this is this is a really nice example. I call it the golden crown because it's really a nice model, I think. Almas, my student, has developed some gigantic models also, but I give a chance to somebody else to show their work. So this was done mostly by a student called Hossein. He's a postdoc still. And the first version is published in Mario's journal, where he's the editor-in-chief. And you can just click there and it's open access, and what you have here is like 79 nodes and 10 different components, and it's deployed in the first version in 11 cores of the Imega simulator. And where you see here wind is a wind turbine. You can see somewhere a battery. I think this is energy storage. No, this is an energy storage. You have some PV. You have protections in the model. So it's really, really a nice model, and the aim is that you have transmission, medium voltage, low voltage, and residential low voltage. So you have three-phase and single-phase, and so on. So it's a really nice model to try to understand active distribution networks. A little bit more work has been done recently with Christian Dufour, actually the guy from OPAL-RT that develops the Artemis library. And this methodology that we have here is called stop-line decoupling, which introduces errors into the simulation. So we thought that we should get rid of that. And this SSN, State Space Nodal Solver from OPAL, was used to implement this model. So now not only that we get more accurate results, but we also use less cores. So this is down to 7 cores using this technique. So that's really nice. It will be soon a release in RT Lab in the libraries from Artemis. But if you don't want to wait, just go to GitHub. Here's a link, and you can download it and play with it. It's released on the GPL version 3 library, so make sure that you read what that means. Okay, you're supposed to make things, if you're going to distribute some new version, you have to make it the source available to everybody else. All right, so now you have the model ready. So what are, there's not such thing as a real-time monitoring application. There's useless, because you cannot react in real time. You have near real-time monitoring applications, and this aims to provide fast updates in near real time. So 10 seconds, I would say, or tens of seconds to a few minutes, when the reaction still is possible with a human being. Okay, so this is near real time, because real time is 1 second equal to 1 second, and then if we talk real time in terms of the loop cycles, then you're talking a few tens of milliseconds. So using a library that we'll show later, we have implemented all of these different applications. You have monitoring and visualization. Here are the references that you can take a look. Some mobile applications. So this is a really nice hack, because once we had our toolkit in LabVIEW, we just used LabVIEW toolkit to implement these mobile applications, and it was really fun. We have these inter-area oscillation tools. There's one coming soon that it's going to be open source. Maxime is doing that. And we have this force oscillation detection when subsynchronous wind farm oscillations. This was Maxime's master thesis, and it's one of the projects where we have really gone through the whole model-based development approach, actually. And finally, here you have a real-time voltage stability assessment that was presented in some conference, but we haven't written a paper, so hopefully Jan will write it soon. So that's for monitoring. There's a new application here using this model. So the idea here is that you can monitor transmission and distribution grids at the same time and decouple their contribution to voltage stability. What does that mean? It means that you can tell who contributes to the voltage stability of the system. So this is the transmission network, and we're monitoring with PMU1. So it looks at the input of the transmission network. And here you have the distribution network, and you're looking at it from this aggregated load. You have another PMU. So you are able to decouple actually the network. So what happens is that we don't have this wind farm connected. So you can see the effect of both networks is the yellow one, and the effect of both networks is actually some sort of combination of the effect of the distribution network and the effect of the transmission network. So actually the limit really of the stability of the whole system, if you assume that we have some sort of noise, saddle noise bifurcation, it's more or less driven by the distribution network. So what happens when you connect the wind turbine? Well, voila, it turns out that you have increase on the total stability of the system, and the indexes of instability are decreased everywhere. And why is that? Because you're providing reactive voltage compensation from the wind turbine. You're controlling the voltage, so you're letting the power flow through, more power to flow through here, so your margin increases. And this is a really nice way of how you can understand an active distribution network, how it impacts in different ways, but also the value of PMU data to monitor these sort of situations, because if you lose a wind turbine in this case, you're really going to decrease the stability of the system. So if you were operating here and you lose the wind turbine, you're pretty much going to have a problem. All right, so you can read all about this in this paper. It's not yet in IEEE Explorer, so you can click on this link and you'll get it. Okay, real-time control and protection. So real-time control and protection are actions aiming to steer, optimize, and protect the overall system in the time scale of a few milliseconds to tens of seconds. This is completely different to the reaction time of control room operators, which uses data from 2 to 5 minutes, and if they're lucky, they have some PMU that is a little bit faster. So if you have this time scale, you actually have to keep latency really minimum, and these applications must act automatically. When you hear about power system control, forget about control design, forget about all these things. You have to think about embedded system limitations, okay? This is what you're going to have to deal with. So the approach that we had here with Almas, my PhD student, we started, well, didn't these things in order, but this was the philosophy behind it. The philosophy was that we're going to convince anybody that our controls are as good as anything out there. We have to be able to show them that. So the first thing was to test and assess the stability provided by a standard PSS. So there is a paper here that goes through all of these details, and you can look at the PSS functionality of the multiband PSS. Okay, so we want to implement wide area dumping controls. So we gotta be better than this PSS that functions locally. So the next stage was to develop all of the models to use in a real-time simulator for real-time software in the loop simulation, so we could derive requirements for real-time hardware in the loop. So the models implemented include the multiband PSS of this guy, and also the so-called phaser POD, that is the algorithm that we want to use for wide area control, because you don't need a model of the system to try to damp the oscillation. Most of these methods to calibrate, then you have to get a model of the system, and if you try to extract a model of the system from one of the e-magazine models, good luck getting a linearized model. It's really hard to get anything out of that. So you have to treat this stuff here like the real system. So that was our approach. So this was implemented and tested in software in the loop with all of the models here were developed by Alma. Some of them were just modified from the library, but for example, this one was customized, custom made. And then the next stage was, okay, now we have the models and we have this excitation system that has a PSS. So what we did is that we tested the excitation system with the PSS model that we have implemented, and we compare it with the model, with the actual function of the PSS here. So what we're doing actually here is that we're feeding an excitation system, the equipment that you have in the field, an external signal, okay, from a damping controller. And these are all of the controllers that we tried with this approach. So this naturally allows us to take one more step, okay? So here we had all the Kunder system stuff, and we have this controller. So now we can take the final step and implement that, the stabilizers on hardware. And here are 3 papers where you can read about this first, let's say the first attempt that we did at all of this. So to do a control implementation, you start from the software in the loop results, and you get an idea of the dimensions of your equipment. But I mean, the design that you had is going to have to change. Why? You have some initial specifications and some initial requirements through software in the loop. But then you're going to have to try to implement them, and you're going to face technical limitations of hardware. You're going to face processing limitations of hardware and software. So you might not have the functions that you need, and then you're going to have to change the requirements and revise the design and go iteratively around this. So this was the first design where we wanted to have everything in the real-time controller, the parsing the data, selecting signals, processing signals, implemented the wide area damping function, and simply interpolating with the FPGA to generate an output in digital form. But this was not possible, actually. We didn't have the protocol parser so that we can run a controller inside of the real-time system. So we had to use a non-real-time computer to deploy the real-time data mediation, the signal processing, and deploy in the controller the wide area control function and leave interpolation. Well, we had some additional problems, and we actually had to change this again. So more or less the final function was that we had the data mediation here, then we had the selected signals for the controller were communicated with shared variables in LabVIEW, and we had to implement the damping control algorithm in the FPGA and wire out with an analog signal into the simulator. And this is the final architecture that you will see in some of these papers. This is the S3DK toolkit where we implemented these parts. And this has a 20 milliseconds loop rate because you get phasers at 20 milliseconds. You have some network communications, and the real-time controller had also the same loop rate of 20 milliseconds. You can go down to 10, but that's it. So we needed 50 microseconds output because the simulator is running at 50 microseconds. And this guy's thesis, Elric Revello, shows that if you don't have the same loop rate or multiples of the loop rate, you will have numerical oscillations when testing the algorithm. So what we implemented at the end, you can see here the control configuration interface. So you're talking here into this box, the Compact Rio, and you can see here which kind of signal. The signal we're using here is a positive sequence voltage difference. So you're taking two phasers and using the voltage difference for that. And here you have the control configurations. It's a simple PID actually, but how you configure it, but there's more details on the papers. Here you have the layers. So you have the FPGA layer B here, the layer A, and this layer is the S3DK that you will see later. And to test it, basically we had the real-time simulator, analog to, digital to analog, we had a PMU, we had TCP connection, a PDC, TCP, this S3DK software, and the controller generated analog data. And the proof is in the oscilloscope, I like to say. So here you have a nice experiment where we actually got the result. All right, so finally we were, okay, now we can actually, if you look at this, the way that we build this architecture, my idea was to have a generic system. Why do you need a generic system? Because I don't want to make 1,000 of these things. I just want to make one box that you can configure and insert here into the auxiliary signals. And it can be controlling anything, a generator, an SVC, whatever. Why do you have to have a dedicated box? And so the idea in the next work that we did was with this student, Gudrun and Almas and Maxime also, was to extend the application to do load control. So actually it was really a nice idea from my students. It was not my idea here, but the idea was to use this phaser POD to generate the signal for damping that is generated by this controller, and actually detect the maximum and the minimums to use it as a type of load modulation on and off. So this was the controller that was implemented. In this case, we took these layers, they were cleaned up a lot and fixed, and additional control was implemented, and it was tested in software in the loop and hardware in the loop. So the nice thing, if you look at this example here, is that you have two types of signals, voltage angle difference, and just the voltages from a specific location, and you have software in the loop and hardware in the loop. And people ask me, why is hardware in the loop not better? Well, the answer is that you have hardware in the loop, and you have delays, and you have noise, and you have a lot of things. And all of the stuff that you have in hardware in the loop, you will never see in a simulation. And these are the kind of learnings of what we're getting out of this. We're starting to understand all of the limitations, all of the real problems that we have to cope. So this is an extremely good learning experience, I think. So I don't know how much time I left. Yeah, I'm slightly over. Okay, so, I'm gonna just point out.
You're over,
by
10 minutes, but just so you know, you only lost 5 people out of 110. So we'll let you continue.
If the audience doesn't matter, I'll keep going, because if I haven't bored you now, I won't bore you with the rest. All right, so the last area that I want to show you is that this is Almas's PhD work, And it's how do you do protection, wide area protection? And there's people talking a lot that you have to have this PMUs and PDC and doing all this big infrastructure. And I think that's rather silly, actually, because protection should be a little bit simpler in a way if you're going to depend on it. So we looked at this islanding because it's really interesting, and there's severe problems in the northern Norway where we used to work with them. So we wanted to do islanding detection, and this standard for DG says that it should be in 2 seconds, including the detection of the islanding, trip signal generation, and trip signal transfer. So to do this, we need to have a detection zone. So it's this range of powers mismatches between the DG supply and the load. And this will tell you if the method will fail or not. So there's 2 ways of doing it, with local measurements, the traditional way. But these guys have a large NDC. So you will fail if you don't have a substantial mismatch. So what about using wide area measurements or just remote measurements? Okay, so you can use one at the network and one at the DG. So here you have the idea that we have one at the network and one at the DG. So the hypothesis is that we should improve the detection time because we have better ability to detect imbalances if and only if the delay is controlled to a minimum. So what is this delays? Well, both measurement and signal trips will have delays other than the and this should be kept as small as possible. And then which methods should we use? Well, we don't know which one will work better, so let's try them all. So this over-under voltage, over-under frequency, and runoff. And let's try them on their local and wide area measurements. And how do you minimize the delays? Well, the proposed approach was to minimize the delays by doing direct relay-to-relay communication using the PMU data. So basically you have a master-slave configuration. And then use 61850 to isolate the DG and trying to minimize the delay trip time. So here we have, that's why the approach is a hybrid synchrophasor and goose approach, because we're combining synchrophasors with goose. So what Almas did is that since you see here, there is no special library, nothing to parse. So this was implemented directly on the relays. So here is the implementation of the algorithms. I'm not going to go into details. You can go to the paper. But there's one for local phasors and one for remote phasors. And you have here the way that we did the test setup. So here you have a trip signal for the local case. And here you have a trip signal for the remote case where there is a direct relay-to-relay communication. And here you can see, this is the voltage, over-under voltage implementation in both cases. So you can take a look at these equations, how it works. It's very much this logical block diagram. So what's the result? Okay, so first of all, local over-under voltage islanding and wide area over-under voltage areas, they have a different NDC zone. What this translates to is that, as you can see here, the blue line, okay, the blue, it's for the over-under voltage, and as you can see here is the 2-second threshold. And what happened? Well, that we actually minimized, we reduced the tripping time in total under a mismatch of 40%. And not only that, it operates with a smaller mismatch. So this is what is shown here, that our non-detection zone is actually reduced with respect to local phasors, and that's of extreme value, I think. So it's very effective, but the most effective one turns out to be the runoff-based one, which has only a 10%, not even 10%, is less than 10% non-detection zone. What that means is that you have to have very little imbalances in the system when you're using wide area measurements. Okay? So the general conclusion of the paper, or the most important, is that the wide array schemes do not only perform faster, but also have smaller NDCs. And we found out through 400 real-time hardware-in-the-loop tests that if you keep latencies to a minimum, these passive island disease schemes reduce the non-detection zone from half to 2/3. So an improvement of 50% of more. So this is really a business case to use wide array protection, that you can improve 50% or more. That's a huge selling point. So if you're having problems, people believe in PMU protection, this is a great experimentally shown case. And finally, I'll show you the tools, really just telling you what they are and where you can find them. Why do we make tools? We're not software engineers. Well, we ended up in this situation that we had all the infrastructure in the lab, okay, PMUs, the network, the PDC, the protocol, but the real-time data was locked into a vendor-specific software system, and the historical data is generally in a proprietary database. So I actually thought we really need interface using standard protocols and a flexible development environment so that we can actually implement something for ourselves. This traditional approach, in the traditional approach, the road is closed. But if we have some tools, the road, you can take the next step to walk the last mile, as I said. And you have to keep in mind of our context is that we actually have students and researchers that do not have proficient C++ programming skills. So we need to get people within 6 months doing something new. So we needed this flexibility. And this is a story of more or less also the 5 years that we've been doing work. So we started with different tools. So we have one called Babelfish version 1, Babelfish LabVIEW engine. And this works with ActiveX and C++. This one is LabVIEW only. This one is our main toolkit. It's the most user-friendly one. And it also has an advanced programming interface so that you can use it in LabVIEW, but you could also use it in other stuff. This is the S3DK, so this is something important. But why did we keep going after having this really useful one is that, well, it only worked on LabVIEW, and it didn't work on embedded computers, even the National Instruments ones. So then we developed this LabVIEW only engine so that we could use it within the Compact Rio. But then I want to make things for distribution networks and rural electrification. So how am I supposed to make that if it's so high cost? So the next stage of our work is to go support the newest standard, 61850-90-5, and be able to deploy and prototype in custom off-the-shelf computers. So this is what we're going towards if I get grants. If you can help me get grants, please talk to me. This is a slide that shows you the performance and functionalities between the different tools and the user friendliness. The most friendly is this one, but it doesn't support any embedded system, while Corgin, our most recent library, supports, well, it's built on C, so you can run it on anything. We have tried it on the Raspberry Pi and it works. So these are really nice tables so you can understand this mess that we have made. Just for you to take a look, this is the graphical user interface of the S3DK. This is the LabVIEW API. This is actually calling the LabVIEW API. You have the user interface is this and this, and you have tools. So here it allows you to see if you're connected to the PDC or the PMU. Here you configure the connections and you do the connections to the PDC of the PMU, and you have a bunch of this type of blocks that allow you to use the signals within the LabVIEW environment. And where we use these tools is that we use them mostly on any computer here, the S3DK, Babelfish, or Corger. They can be deployed in any computer using Windows. This one in any computer. And then the Corgin can be really run anywhere. And to look at the example, this is the controllers that I showed you before, the load controller. This was done with S3DK, and this was the architecture. Now that we have Corging, we can replace this non-deterministic delay by running it in a real-time processor at 20 millihertz loop rate. And what it results is that we remove the problem of the non-deterministic latency from the computer, and you can see that we are able to stabilize the system faster. The blue one is the one with S3DK, and you see that it has a lower performance on damping. Of course, you can never beat software in the loop because you have hardware in the loop. You have delays in the system, but we decrease the delays for over 100 factor.
Hi,
So
sorry, Luigi,
that's it. Here's the links.
We went up a lot.
Yeah. So here's the links with all of the papers. Here is the GitHub repositories where you can find it. There is other GitHubs for other tools that I didn't talk here. And here's the conclusions. I'll let you read it yourself while Tom talks now. Sorry for taking so long, but I didn't time myself.
No, it's fine. So, so just so everyone knows, we will make the presentation available online. I believe Mario and Luigi are going to allow the slides to be made available as well. So, and of course, you can always contact them directly. Their emails are here, but you can look them up. They're public. Anyway, if you would like to contact us, you can always go to our website. We'll be at NASP in Seattle in October. We're also on LinkedIn. So, and of course, you have the contacts of both Mario and Luigi. Just remember to take the survey as you leave, because as we saw, we definitely have a lot of material to talk about over webinars. So to help influence the choice of the next webinar, please make sure you fill it out with your preference on the topic, and we'll be able to bring you another one hopefully in the next couple months. So in any case, thank you very much for your time. Thank you to the presenters, the attendees. Everybody have a great day or evening wherever you are.